This is a presentation of SBE 15, New York City.
Thank you very much, Conrad and Jeff. I appreciate you inviting me this evening to speak about what I'm doing and some of the things that we can do with drones these days, specifically for tower work and broadcast inspection, particularly infrared. That's what I'm really going to be talking about tonight. I know we've all heard about drones, being used for tower inspections, and I'll talk a little bit about visual tower inspections with drones. But the main thrust of my presentation this evening is talking a little bit about infrared imaging, how we can combine it with drones to use it for useful purposes to help us diagnose and keep an eye on transmission systems on towers that are sometimes difficult to access by our mere human beings that don't climb towers. So it's been very interesting. I've been doing this for a couple of years now and have some interesting results to share with you. So we'll talk about that. But first, I wanted to give you a little background on myself, who I am and what I do. As Conrad mentioned, I opened my own business a few years ago called Shulins Solutions. And before that, I worked for a couple of years for Burke Technology as their CTO. And they, of course, make all kinds of great remote control stuff. And then before that, I was with Greater Media in Boston, heading up 5-station FM cluster there, and I was the director of engineering for the local area there in Boston, building some of the first consolidated facilities back in the late 90s. So, but basically today, my company, Shulins Solutions, is built on 3 pillars. I do RF system monitoring with a product called Stellar Eclipse. And if you go to shulinsolutions.com, which is going to be listed on this presentation at the end, you'll be able to find out a lot more about it. But it's been particularly relevant these days with the TV repack, because there have been a lot of problems with infant mortality with transmission line systems and antennas as these repacks come on the air. And basically, one of the things that we found is the VSWR foldback systems in many TV and radio transmitters are not adequate to protect transmission lines and antennas from burning up under bad conditions. And that's a presentation for another day. But in a nutshell, it's worth really looking into making sure you have hard interlock protection for your transmitters, whether you're in a combined situation, a multiplex situation, or whether you've just got one transmitter into one antenna. It's really worth it to make sure that you've got some kind of monitoring and protection there, because obviously these things can be very expensive to repair once they happen. Second pillar is SUAS drone inspections, which we'll be talking about a little bit tonight. And the third is just in general broadcast technology consulting to meet the needs of broadcasters, and again, specializing in remote control solutions, studio design, and antenna systems, as well as some of the work I've done with PPM metering and research into how the PPM signal gets encoded, and more importantly, under what conditions it's impaired. And one more slide here on a little bit about Stellar Eclipse. And basically, a reminder that it's really important to, if you don't have some protection on your system, to think about putting it there. So let's get on to what I really wanted to talk about tonight, and that's infrared imaging and how we use it with drones and how it can help broadcasters. So a little bit of quick background here. I took a course a little while ago, and I'm a level 1 certified thermographer. And during this course, I learned a lot about infrared that I really didn't know, and I hope to share a little bit of that with you tonight. A little bit of the history here is that it was discovered in about the year 1800 by an astronomer, William Herschel. He used sunlight in a prism, and he was one of the first people that really realized that different colors represented different temperatures. And he also realized that red light was the warmest, and the area beyond that red was even hotter. He also discovered the planet Uranus, and he used a visual telescope to discover that planet. And he also did some very early work on spectrometry in the late 19th century. And that helped us understand the composition of deep sky objects, stars, and other deep sky objects. So what is infrared? Well, the definition is it's classified as electromagnetic radiation, just like we know light is and radio signals. And it's longer than visible light, generally invisible to the human eye. It starts at about 700 nanometers and goes to about 1 millimeter. But there's no hard limit to what's visible to the human eye because sensitivity drops off pretty smoothly at around 700 nanometers. So sources longer than 700 nanometers can still be seen if the light source is sufficiently bright. And that, of course, creates a danger to human eye tissue because you can get heating there. And we all know that heating human tissue cannot be a good thing and is not usually a good thing. So it's one of those hazards we have to think about when we are dealing with infrared radiation. One of the other things that may not be familiar to you is the concept of emissivity. And in order to understand how infrared images work and what they mean, we have to know a little bit about emissivity. And emissivity is a measure of how efficiently an object radiates heat back. In other words, how well the surface of an object will tell the truth about its temperature. And so emissivity values are defined in a narrow range from the number 0 to the number 1, where 0 is a perfect mirror that reflects all energy, and 1 is a black body that perfectly absorbs and radiates all of its energy. So in general, what you need to know is the emissivity of the target that you're trying to measure. If it's below like 0.5, you're not likely to get an accurate temperature measurements. In these cases, you might need to find ways to increase the emissivity. And I'll show you on the next slide some of the clever ways to do that. But emissivity in general is one of the tougher things to understand and one of the more challenging factors to be aware of when taking temperature measurements. It can be, however, compensated for. This slide actually demonstrates what I'm talking about. High emissivity surfaces like electrical tape can be used to accurately measure the temperature of low emissivity surfaces like shiny metal. For example, on the left here, you see a visual image of a couple of paint cans, and there's a piece of electrical tape on the one on the left, and there's a piece of a different type of plastic tape on the one on the right. And if you look at the right-hand image, you can see the electrical tape shows up very differently, especially on the left can than the rest of the shiny surface. And this was taken with an infrared camera that has a spot temperature meter. And you can see that the temperature right in the middle of the electric tape is showing something like 163 degrees, whereas if you're looking at the shiny can part, it's only showing 74.3 degrees. So which one is right? And the answer is the one with the high emissivity is right. That's the electrical tape. So I show this because if we think about a transmission line, well, what's the outer conductor if it's rigid? It's made of copper. And usually that copper, if it's new, is pretty shiny and emulates what you're seeing here on the paint can. So the temperature of that would not be representative of the real temperature on the surface of the transmission line. You'd need to put a label on it, or you'd need to put something with high emissivity on it, like a piece of electrical tape, and shoot that. So I've listed here a few different samples of emissivity for different materials. And of course, at the top, we're most interested in copper because that's what the outer conductor of rigid transmission line is. And if it's polished new copper, you can see it's a very low number there, 0.05. But if that copper is oxidized, it's not so shiny anymore, the emissivity goes up to 0.65. So that would be a much better indicator of what's going on with the surface temperature. And here also is listed a few other sample substances. These are all published, and there are places where you can see different types of material and the emissivity values that are listed. And the idea here is that if you know the emissivity value, there are ways to calibrate the image that you're taking with an infrared camera and get actual temperatures. And by the way, I will be, pausing for questions, so keep those in mind as we go forward here. So the application for SUAS in broadcast engineering, basically qualitative versus quantitative thermography are defined here on this slide. Qualitative thermography is using thermography skills and training like someone has if they're certified thermographer to understand those images, much like an X-ray technician would be trained to understand how to read X-rays. It's the same kind of thing with infrared. You really do need to know, how to read those images and how to discard information that may not be valuable. So qualitative measurements are made on objects like solar panels, rooftops, and broadcast transmission lines and antennas, where quantitative measurements are getting those actual real numbers and numerical measurement reports using calibrated instruments, and that has to be in a controlled environment. So examples for that would include indoor stuff like taking the temperatures of motors, electrical panels, and human subjects. Recently, we've seen a lot of stores and places scan foreheads before you go in, and in a controlled environment, you can get pretty accurate temperatures with infrared looking at objects inside. So a little bit about the theory of how this stuff works. When infrared energy strikes the detector, it actually heats it up a little bit, and that changes the resistance in the chip. And these resistances are measured and ultimately processed into digital signals rather, used to create the images on the display. So the infrared image, usually the chip is made of vanadium oxide or amorphous silicon resistors. And again, those resistances change as the infrared energy strikes the detector. Oops, I'm going double clicking here. Okay. So for general drone usage, we use drones for a number of different things in broadcast engineering. We use it for visual tower inspections. We use it for infrared scans for heating, which I'm talking about tonight. We use it for RF signal measurements, in place of ground-based measurements and helicopter measurements. This has proven to be a pretty efficient way to verify antenna patterns and so forth, as well as thermal imaging of AC power panels inside. So those are kind of the four major things that I think that SUAS drones are used for, with the exception of the bottom. We usually don't use a drone inside to measure the AC power panels, but that's with a stationary camera gun. So why do we do this? And the idea here is that we don't get to see the heat really on the tower, right? I mean, it's in a range of electromagnetic radiation that our eyes are not sensitive to, so we can't capture it in a traditional photograph. And so I think of it as giving us a sixth sense of what's occurring in and around our electrical and RF systems. And the more we can understand about the environment and what's happening with our systems, the better we can actually end up taking care of them. So I kind of view this as another dimension that we can look at to gauge the condition of the system and what's going on. And of course, the application here with infrared is transmission lines, antennas, RF patch panels, RF combiner modules, RF switches, and the power panels. So the definition of SUAS, we talk about SUAS and drones interchangeably, but they're really a little bit different. SUAS is defined as a small unmanned aircraft system, and it, of course, consists of different components. One of them, of course, is the drone, the unmanned aircraft. It's got to weigh less than 55 pounds to qualify to be in that category. And it also includes the system on the ground connecting the operator to the UAV, which would be the joystick controller, the radio controller, and any other associated hardware, as well as the operator on the ground. So it's a system. That's why it's called SUAS. So using drones for imaging, we use these small aircraft to inspect areas on the tower that are not easily accessible. It's safer and less expensive than a tower crew. It also gives us the ability to fly in a wide range of weather conditions where tower crews would not normally be available to climb. We can also set these things up on very short notice, and we can provide distinct views from areas above the tower looking down and other perspectives where a human being would not necessarily be able to provide those different viewpoints. So it's not all easy to do. Of course, there are practical and regulatory operational considerations. And, to do this kind of thing does require a Part 107 pilot license to operate the drone. And it also requires a second person as a qualified spotter. One of the things that you learn is that basically you just can't fly the drone and be looking down at the data coming in and also glancing up at the drone. We need someone to actually have their eyes on the aircraft 24/7, full time. You can't take your eyes off. And it has to be a visual contact. You can't use binoculars or anything like that. The drone has to be within visual contact at all times. Most often, it requires some FAA and local approvals to fly above 400 feet above the ground. And I do that through a subscription with a company that owns a lot of waivers around the country and is able to sell those or rent those waivers to me whenever I need to fly in an area where those are required, which is most of the time. And of course, liability insurance is an important thing, and hull insurance. Liability because you want to be covered in case there is damage from the aircraft hitting a person or property on the ground, and hull insurance because these drones, especially equipped with these kind of payloads, can run anywhere from $30,000 up. So it's a pretty expensive piece of equipment, and you want to make sure that that is all covered. So in terms of flight conditions, some of the things that you have to look at is the weather forecast. Wind speeds need to be within tolerance, and that tolerance does vary with the type of equipment you're using and, of course, the skill of the pilot. And just like flying an airplane, you require ceiling and visibility clearances. It's got to be VFR, Visual Flight Rules. And for the infrared imaging, it is ideal to fly at dusk or dawn to minimize solar loading. And when you think about that, it really kind of makes a lot of sense, because if the sun is beating down on the tower, there's a lot of extra thermal energy there, and you're trying to detect small changes in temperature along a transmission line or along a tower. And the sun can basically drown a lot of that out. So I try and fly after sunset or before sunrise, but not when it's so dark that you can't see the guy wires and the tower. So the ideal time is when the sun's a few degrees below the horizon. Also, you can fly on an overcast day if it's kind of dark and gloomy and there isn't a lot of solar radiation beating down on the transmission line. And of course, the flight should always take place when all stations are operational, so that the maximum or normal amount of RF energy is present in the transmission line, so you can see if there's any loss where there shouldn't be. So a lot of people ask me, well, Paul, this is all interesting, but I'd be pretty nervous flying a drone around, several hundred kilowatts or even megawatts of RF energy. And so how do you deal with that? And the answer is basically using a drone that's well shielded, using a drone that has redundant communication systems and redundant control systems on it, as well as a technology called RTK. And RTK technology, I'm going to explain in the next couple of slides, but basically it involves using differential GPS corrections, and it basically takes a lot of the sensitive compass type stuff out of the drone aircraft and puts it on the ground so that it's not affected by the RF. And of course, you do want to fly as far away from the radiating elements as possible to still obtain useful resolution. And we get into a little bit of that in a couple of slides that are coming up. But basically that involves choosing an appropriate focal length lens for the camera so that you can get close enough optically, but you can stay far enough away physically so that you're not saturating the aircraft with RF. And of course, using caution for guy wires and other obstacles, and never flying over people or animals is important as well. So I mentioned RTK in the last slide. What is RTK? It stands for real-time kinematic positioning. And basically this is this differential GPS that I was talking about. And it obtains satellite signals and basically broadcasts these corrections to the drone independently of the operator. So you can see the diagram here on the right-hand side of the screen. Down here is a tripod with the RTK device, which is generally located within a quarter mile of the operator on the ground. And it receives its correction signals from the satellite system. And those GPS coordinates get transmitted to the aircraft both by the satellite directly and by the RTK base station. This basically allows the drone to be positioned within centimeters, or I guess I should say more accurately, it allows us to know the exact position of the drone at all times within a few centimeters. However, the drone may not stay within a few centimeters of where you put it due to environmental conditions like the wind, for example. But it does greatly enhance the stability of the drone, and you can fly in a wider range of weather conditions than you could if you didn't have the RTK. But the main purpose I use it for is really making sure that these control signals get to the drone without having to worry about the RF so much. And so, some of the benefits of using this RTK technology include pinpoint accuracy, a little bit less concern about the winds, the compass being away from the aircraft, and always knowing the exact position, and in general, much more accurate hovering and positive control, even in gusty conditions. This RTK is not something that can be added to just any drone. The drones need to be manufactured to accept these kind of signals, and generally, they're sold with those accessories available. And this is kind of what it looks like. This is the remote base station for the RTK that I use. It's on a surveyor's tripod. Like I said, it's generally located pretty close to the operator. Sometimes it can be up to a quarter mile away. It runs on its own battery, which you can see halfway up the pole there, and that generally runs most of the day. And then at the top is the square, which is the GPS receiver and the radio transmitter that links up to the SUAS drone. So one of the surprises that I was kind of disappointed in, but really happy to learn, was the limitations of what you can do in an uncontrolled environment, especially when you're doing infrared imaging. And I found out that it was meaningless to specify or compare precise temperatures when you're shooting stuff outdoors, like a transmission line on a tower, for example. And the main reason is wind. because a wind that's only going 3 miles an hour can actually cut the temperature reading in half that you're looking at with the infrared camera. So you're never going to be able to, unless it's perfectly calm out and you've got a great environment, you're never going to be really able to take thermal measurements of an antenna and transmission line, log them, and then come back a month or a year later and compare them to what you had. It's just not going to work. Those qualitative measurements are worthless. So the real value of this is to take pictures and detect uneven or unexpected energy loss, and not so much to look at the absolute value of those readings. Some of the other things that you look at are the angle of the acquisition, and it's critical, and it really requires an angle greater than 60 degrees. If you're at less than 60 degrees, you can get some nasty reflections, and basically you're not sure what you're looking at. So that's one of the things that is important. And of course, we already talked about emissivity. Emissivity is important to understand because it will provide or supply dramatically different thermal indications. So it's possible to look at the image and identify labels and other surface material to avoid misinterpreting the data. And what's really kind of useful there is to also take in parallel these visual images. So let's say you're looking at an infrared image of a transmission line and you see a spot that looks really funny. It looks like it's a lot hotter or colder than the rest of the line. Well, if you have a visual image of that, you can look at that and say, oh, there's a label there. It's a paper label. And because paper has a different emissivity than copper, you're going to naturally expect a much different temperature reading. And if that's the case, then you really don't have to worry about that, because it's really the emissivity that's giving you the different values and not an actual temperature difference. So I was talking about how close you need to be to get a good image of what you're looking at. And then we get into talking about spot size ratio. And that has to do with the focal length of the lens compared to the distance and the size of the target that you're trying to measure. Unfortunately, all the infrared cameras that I'm aware of that mount on drones, especially those made by FLIR, have fixed focal length lenses, and they come basically in 4 sizes or four focal lengths. 9 millimeters is the widest, and 25 millimeters is the most telephoto. And so this forces you to make a decision when you purchase something like this of what kind of work you're going to be doing. For example, if you're looking at solar arrays and a big rooftop, you probably want something that's a little bit wider, like a 9 or a 13 millimeter lens. Whereas this type of work on a tower where you're looking to stay as distant from the radiating source as you can, but still get the resolution you're looking for in the image, you want a higher focal length. I ended up choosing a 19 millimeter focal length for my camera, which is a bit of a compromise, but it allows sufficient resolution for this type of work. This is a photograph of what I am using. It's a Matrice 210 RTK drone. And this particular drone has dual redundant communication systems, batteries, and as you can see, it can handle 2 payloads. One is a visual camera with a large optical zoom, and the one on the right is the infrared camera, which also has a 4K RGB imager for regular RGB imaging as well. Here's a little closer view of what I use for the infrared imaging. It's a FLIR. The model is an XT2 camera, as I mentioned, with a 19 millimeter lens and the 4K RGB imaging. The resolution is 640 by 480 on the infrared side. It also can take movies at 30 frames per second, which allows you to fly up the tower and capture 30 frames per second with the infrared imager. And again, as I said, it's important to choose that right focal length for the type of work you're doing. And that's what I did, choosing the 19 millimeter lens, which gave us that decent resolution. This camera and most infrared cameras produce what we call radiometric images. Radiometric images, if you're not familiar, are basically JPEG images, but they have a lot of metadata inside them, and a temperature value is basically assigned to each pixel in the image file. And detailed information is available there. And you can really do a lot of quantitative evaluation in post-processing of the scene. FLIR Tools is a great product for that. In fact, it's free. You can download that software from FLIR. They have several flavors of it, but the basic one is free. And this image here that you're seeing on the screen gives you an example of what you can do with that software. You can put your cursor wherever you want and get real, temperatures, so you can see the differential and so forth. Now, again, these are quantitative measurements, and as I mentioned before, these would not be applicable to tower measurements because there's too many variables with being outside and the wind and humidity and so forth. But for circuit breaker panels and anything inside, these radiometric images are really detailed, and you can get some very accurate numbers out of them. The other payload that you saw on the drone was a DJI Zenmuse Z30 camera, 640 by 480 resolution, but the real power in this is a 30 times optical zoom, as well as a 6 times digital zoom on top of that. It may sound like a poor camera if I tell you it's only got 2.13 megapixels, but I'll show you some images from this, and really where it shines is the fact that that 30 times optical zoom can give you some incredible detail, even at a distance of 15 meters from the tower. Pretty amazing stuff. This is a little bit of the hardware that I use along with the drone. It's a Sendence controller and what they call a crystal sky display, which is easily visible in bright sunlight. Each of these devices uses discrete batteries, so that it lasts quite a bit longer than the drone does. My fly time with the drone is about 24 minutes, and the batteries in the display and the controller go for about a half a day. And they're quick change batteries, so it's easy to recharge. This is what the flight deck looks like typically. You can see the base unit, the RTK unit on the right here, a little helipad, landing area. I generally cone off the area and basically use hard hats and safety vests, taking all this safety stuff very, very seriously. Those propellers spin at high speed and they've got some serious torque to them. So we want to just make sure that everybody stays safe on the flight deck. We have emergency numbers handy, ready to go, and a first aid kit. So safety is paramount here. We've never had any incidents, but we don't want to take any chances either. So here are a couple of examples I wanted to share with you of infrared imaging that I've played with. This is a cellular array at 150 feet above the ground. You can't really see the antennas too well, but you sure can see the electronics that show up in the background that are much warmer than the environment. This is a base of a tower. You can see the ice bridge on the right and the base of the tower on the left, and how the transmission lines, which are more warm than ambient temperature, show up quite clearly on this image. Also, on the lower part of the image, you can see a bright rectangle there. That's actually a telephone pole in the background, and that is a transformer that is showing up bright infrared there. So one of my favorite stories that I like to tell is about this system in Boston that was experiencing, it was a multiplex TV combiner system, and they were experiencing VSWR hits, but on a very irregular basis, like maybe once a month, once every 2 months, once every 2 weeks. It was just really random and all over the place. And hired a guy to come in with a TDR, and we did line sweeps and everything and compared them to the original install, and couldn't really find anything that was going wrong. But yet these VSWR hits were unexplained, and they kept happening. So you meet with my handy drone. I said, would you like me to fly it and see if we can spot anything? And they said, sure, go ahead. And I went out and flew it. And these images show what I found. It was a foggy night, so I couldn't really go all the way to the top of the tower, but luckily we found the problem way below that. This was at about 900 feet above the ground. And you can see the image on the right is a regular visual image. And I've put an arrow pointing to the hotspot that I found using the infrared camera, which is depicted in the left image. So I was really surprised to see this. I came back the next night and flew it from a different angle and found the same thing, reported it to them, and they hired a tower crew to come up and take the line apart. This is, I believe it's 8 or 9 inch rigid line. And this is what they found. Trouble was there. In fact, they had to replace about 150 feet of the line. And what had happened here was the line was recently replaced, and an O-ring was not seated properly and fell down onto the Teflon insulator, causing arcing. So the stuff really works, and I was really happy to see that we were able to help them out. You can see on this image on the right a lot of pitting and a lot of arcing that was going on. And it wasn't the kind of thing that totally took them off the air continuously, but every once in a while this thing was running right at the edge, and it started arcing, and the infrared imaging was able to see that heat signature and tell us exactly where that was. And you take an image like that, and you can apply different color palettes in post-processing to look at it and see it in different ways. And that's all up to you as to how you want to use the color palettes. But this gives an example of using different color palettes to look at the transmission line piece and see the heat signature in a little bit different way. I wanted to talk about some of the things that are required for accurate image capture, things that you cannot correct in post-processing. And they call that FORD, or focus, range, and distance. And the requirements are that the picture must be in focus. You can't really fix that afterwards. It must be taken in the correct temperature range for the camera that you have, so that the range is able to sense the temperatures you're looking for. Of course, you must be close enough to the target that you're attempting to evaluate, and that comes back to the spot distance that I talked about earlier with the focal length of the lens. And again, these are the things that cannot be corrected later, so it's important to get it right when you're out there flying the drone and acquiring the images. And so there are challenges to the focus. The focus can be degraded by, flying too high or too fast. If the drone is yawing and moving around aggressively, that can blur the image, as well as gimbal stabilization issues and humidity. So really all those things need to be in check in order to get a sharp image, which is really important for being able to make those determinations as to whether something funny is going on in terms of the heat loss. I'm into astronomy, and so basically stretching images is kind of second nature to me. But if you're not familiar with the concept, basically you're able to take the image and in post-processing ignore areas that are not of interest to you. So for example, the image on the left is just a non-stretched thermal image, which really doesn't tell you too much. And then you take that same image and you look at exactly the areas that you're interested in. In other words, for example, the sky is a big part of the image here. We don't really care about the sky. The sky is very cold. So we take that range that we're going to display on our computer and we say we only want to display a certain narrow range of temperature. And that gives us more resolution. We can see much easier what we're looking for. So this is an example of basically taking that image and stretching it to show the area that is heating and that we're interested in. Again, all tricks you can do in post-processing. This is a visual image on the left and a radiometric image on the right of a UHF TV antenna at the top of a tower. And basically what you're able to do here is take a look at the image on the right. And if you look really carefully, you can see some yellow areas. And, this is just a small image on a slide. But if you had the original image, you can really expand it and take a look at where the power dividers are behind the radomes in this antenna. And you're able to see the heating that goes on and the loss that goes on behind the radomes, whereas a visual image won't, of course, give you that. And the power here is that you can take this back to the manufacturer of the antenna and they can look at the blueprints and see exactly where those power dividers are. And you can see if there's anything going on behind the radomes that's normal or abnormal. And it's great to find things that are abnormal and of course bring them to the attention of the manufacturer so that these things can be looked into more carefully. This is an example of an indoor camera that I use to image a piece of 8-inch transmission line, and you can clearly see here where the insulators are, where the Teflon insulators are that separate the inside interconductor from the outer. This is one of those cases where you can use absolute values to get good readings because it's indoors. I mentioned earlier the best time to shoot these images was, of course, after sunset, where it's still daylight according to the FAA, when the sun's about 4 to 8 degrees below the horizon, so there's no solar loading going on, but yet you can still visually see the tower and the guy wires and fly the drone safely. I talked about that visual camera, the Z30, that had that 30 times optical zoom. And these are some examples of images that you can come up with these high resolution, or I shouldn't say high resolution, but high optical zoom cameras. The image on your left is a picture of the strobe on the top of a 500-foot tower. And my point here is you can actually read the label on the strobe if you zoom in. The resolution is that good. The picture on the right is a cotter pin at a guy anchor attachment point about 400 feet up the tower. So you can really get some good images of where the problems are, if there are any, with stuff going on the tower. And while a drone will never replace a human climbing the tower and doing an inspection, what these things can do is save the tower climber time and ultimately make it a safer job for the tower climber by pointing out some of the things that they may need to look at once they get on the tower. So if you can do these kind of inspections more often and in conjunction with a tower climber, it can help save costs and also make it a little bit safer for the tower climber. These are a couple of other RGB images from that Z30 camera. This is a pole. The image on the right and the left is a pole on the top of a 500-foot tower. And you can see the attachment bolts very clearly. You can see that they're torqued down and the washers are in place and so forth. So the resolution and detail you can get is pretty amazing. This is a picture of a taller tower. And after the tower climbers did some work, we noticed some electrical tape holding some transmission lines and jumpers on, which should really be secured better. So the client was able to point these out to the tower crew and say, go back up there and don't use electric tape, use real clamps and make sure these things don't fly around. This video here is a visual tower scan. I'm not going to play the whole thing because we're getting up to basically the time I wanted to open it up for questions. But let me zoom in a little bit here to give you an idea of some of the detail that we can pick up with a visual tower inspection. I think most of you have seen these kind of things before, but this area right here above the FM antenna was the area, and I'll stop it right about here, is the area where that problem was. So you can see it was quite a ways up the tower. And this is a example of the radiometric images at 30 frames per second that were obtained with the infrared camera. And again, this is the taper on the tower, and I believe the area right above the FM antenna is the area that I spotted where the, and there it is right there. I'll stop that, but you can see that bright area here. This was obtained using the movie feature, so to speak, taking moving images and capturing 30 frames per second. You can imagine 30 frames per second, if it takes the drone 5 minutes to go up the tower, that's a lot of frames, and it's all available to you to look at and to examine later in post-processing. So in conclusion, I'd say that drones can be used in many cases to perform all these kinds of inspections. And proper certification is required, of course, usually a Part 107 license. You need to get the airspace authorizations as well. I want to emphasize that interpreting the infrared images can be tricky, and it really does require an understanding of how the heat transfer occurs and how our cameras work. And a good way to do that is to get your level 1, 2, or 3 certification as a thermographer. Which is not a hard thing to do. And I've got some resources that I list in the next slide that can help you out with that if you're interested. Intermediate tower inspections with drones is also a great idea, as I explained. They can help enhance the safety and lower your inspection costs. Here are some of those resources. You can call me anytime or write to me at paul@shulinsolutions.com. Infrared training, there's a couple of resources here. You can get your level 1, 2, or 3 thermography certificates through ITC. Some of those are available to be trained online. I think they're having in person as well these days. I mentioned the FLIR Tools software available at FLIR.com is free. They have many different products, but the FLIR Tools is free as well. And also YouTube has a ton of free great resources from ITC and FLIR. So if you put ITC or FLIR in your search bar at YouTube, you'll come up with some great resources as well. And I want to thank my instructor, Bill Schwan, the Infrared Training Center. Florida Drone Supply is where I got a lot of my equipment. James Stenberg, who is now no longer with American Tower, he's now with Signal, but he was very supportive, and I've been doing a lot of work for American Tower, as well as the Cavels and Jim Leifer at American Tower. So I will conclude there with just a couple of minutes before 7 o'clock and open the floor up for any quick questions we have.
That was awesome, Paul. Thank you. Any questions for Paul?
He mentioned getting local approval to go over 400 feet. And I'm just wondering, say you have like a 1,000-foot tower already there. Does that apply if you have an existing tower there, or who do you contact that? Who do you do that through?
Yeah, that's a good question. Normally, in terms of the regulations, you can technically fly 400 feet above your tower without getting other authorizations. However, the big caveat is the airspace that you're operating in, where your tower is located, and so forth. If you're in certain classes of FAA airspace, you are required to get waivers and let them know that you're flying. And there are resources out there. There is a website, I think, that you can register with to let them know, that you're flying in a certain area and get those authorizations online without having to deal with a lot of red tape, depending upon where you're flying. Obviously, if you're flying over, Washington, D.C. or New York City, there are different, rules in place, and there are so many restricted airspace limitations there that it can take a while to get a waiver. But basically, I think you need to understand the airspace you're operating in and whether a waiver is required or not. Like I mentioned, I subscribe to a service that has those waivers, and it's a good idea to do that if you're going to be doing a lot of this kind of thing. I know that's a long-winded answer, but there are it's a complicated situation, and there are so many different scenarios that it's hard to give one answer for that. But the main answer is to understand the airspace that you're operating in. If you're in the middle of Kansas and you're not close to any restricted airspace, then you can certainly go fly without any authorizations. But if you're in Washington, D.C., chances are it's not going to work.
So one of the main questions I had that you addressed in the presentation was the RF issue. You're flying something that depends on receiving a signal from your controller on the ground into an RF field. The RTK solution seems like a good one, and your backup systems and all. But do you ever find that you just get completely overloaded on the receivers on the actual aircraft and end up not being able to fly a tower?
Not yet, Conrad, but one of the things that is kind of a fail-safe built into the drones is that you can program the behavior if it loses link. And basically what you can have it do is you can have it return to the launch pad, but I don't do that because it could hit a guy wire. So I instruct it, if you ever lose communication with the joystick controller on the ground, start descending. And generally, descending out of the high RF field will allow you to reacquire control and land safely. Has it ever happened to me? The answer is no. I've had some weird readings, because you get like real-time readings of the battery's strength, and I've gotten some weirdness going on there. And basically, when that happens, I descend and bring it down and fly it again further out. I think a big part of it is the shielding, and a big part of it is knowing not to get too close to the radiating elements. And like I was saying, choosing a focal length for the lens that allows you to stay at a safe distance. And typically I'm at, 3 to 5 meters. I don't get any closer than that.
Still, you're up in the field there.
Oh, absolutely. And yeah, these are high power, FMs and TV guys.
So when you say shielding, did you have to do special shielding to the unit, or it comes that way?
It came that way. The RTK, the 210 RTK, and now the 300, and I think they have some newer models, are designed especially for these kind of industrial uses. A lot of times they'll fly these things around high voltage, transmission lines, high tension public utility lines, that kind of thing. So it's designed for that. Obviously, we're dealing with a lot higher frequencies, and we're a lot closer in many cases than we are to power lines. But the point I'm making is, I guess they're industrial drones that are shielded and come that way. They're not impervious. They're not perfect, and that's why I think everybody needs to be real careful when flying around high RF environments. But the point is that it's doable if you're careful, and it can be very useful, as you've seen in some of these slides.
Does anybody else have any questions for Paul?
Yeah,
Well,
hi, Paul.
oh.
Great presentation. I really got a lot out of it. Early on, you mentioned pattern measurements. Is that a separate payload to do a pattern measurement?
Yeah, Frank, it is. I have not gotten into that realm. There are a bunch of companies that do a great job. Six Arms comes to mind. They're an Australian company. And they of course don't fly as close to the radiating elements as I do, because they want to get further out and get decent far field measurements around the tower. But yeah, it's completely different payload, spectrum analyzer, the whole deal. The regulations and the physics behind flying a drone are the same, of course, but yeah, it's a different type of business.
Okay, thank you.
And it's a good business too. Some I'm not an expert in that area, but the cost savings are tremendous compared to doing a helicopter run, or a lot quicker and less expensive than doing ground-based runs as well. Again, a good resource for that is Six Arms. They've done a great job for some people.
Anyone else? Okay. Well, Paul, thank you very much for the very informative presentation. It's a pleasure to have you. Thanks for making the time for us. And Jeff, did you have anything else? Did you want to go over our survey before we close the meeting?
Well, seems like most people were not interested in old-time radio TV shows, so we're calling it for WKRP, and that's what I get for coming up with a question in less than 5 minutes. But yeah, the next poll will be, do you like taking polls? But we'll see everybody also for our tower lighting palooza, and look out for other activities we have, and we'll have this this webinar recorded for you and on demand on the website SBE15.com.
Hey, thanks for the invite. I really appreciate it. Good to see you all, and hope to be in touch.
Thank you so much, Paul.
Thanks,
Take care
Paul.
now.
And thanks everybody for joining us. We'll see you in a month.
Thanks for joining us. Please remember to subscribe to SBE 15 New York City.